Okay. So I'd like to welcome you all to another edition of Quantum Computation and Isolation. So today I'm very happy to introduce Professor Sevag Gharibian from Paderborn University. So Professor Gharibian got his bachelor's degree in computer science at the University of Waterloo in 2005, his master's in mathematics from the University of Waterloo in 2008, and his PhD in computer science from the University of Waterloo in 2012 under Dr. Richard Cleve. He taught as a visiting lecturer at the University of Illinois at Chicago in fall 2012. From 2013 to 2014, he was a postdoc at the University of California, Berkeley. From 2014 to 2018, he was assistant professor of computer science at the Virginia Commonwealth University. And from 2018 to present, he is a junior professor in computer science at Paderborn University in Germany. He's a recipient of many awards and grants, including in 2013, Canada's NSERC Banting Postdoc Fellowship. He was a Simons Research Fellow at the Simons Institute for the Theory of Computing at UC Berkeley. From 2016 to 2018, he was secretary on the board of trustees of the Computational Complexity Conference, and he's the founding editor of the open access journal Quantum. So today he'll be talking about how hard it is to simulate local measurements on ground states of many body systems. So please help me in welcoming either by muting yourselves and clapping or by clapping virtually, Professor Sevag Gharibian.
Great. So thank you very much for the lovely introduction. Just a very quick heads up. I have a kind of a widescreen monitor, so if I look to this direction, I'm looking at the column of you guys, so I'm not ignoring you guys. So thank you very much for the invitation, first and foremost. It's a pleasure to be here, of course, and thank you for the lovely intro, like I said. So just another quick heads up, I'm a computer scientist by training, okay? So however, of course, I realize this is essentially a physics audience, so I've tried to make this, physics friendly, or at least not requiring CS background friendly. But with that said, of course, you're more than welcome to stop me at any time to ask me any question you like, no matter how silly you may think it is, the sillier the question, the better, right? So feel free to interrupt. As Joshua said, this is going to be a talk about the difficulty of simulating local measurements on ground states of many body systems. Okay, it's joint work with my collaborators, Johannes Bausch, Stephen Pittock, James Watson, and Justin Yurka. And here are basically the preprints of these papers. So you're welcome to reference those if you're interested later. Okay, so let's begin. So I'm a computer scientist by training, okay? And in particular, one of the areas I work in is called complexity theory. So what does that mean? That means that you should think of me as a zoologist, right, of sorts, right? And so what we like to do is we like to take our animals, and animals for us means computational problems. And we like to, sort them just like you with animals. So we will take our computational problems and we will kind of classify them in different cages of the zoo, let's say, or however you want to think about it, according to their difficulty, right? So for example, exhibit A in our zoo might be what you see here, this teddy bear, which are, we'll think of as all the problems we like, essentially, like efficiently solvable problems. These would fall into the complexity classes, which you may have heard of, like P, classical polynomial time. BQP is what you can solve on a quantum computer in polynomial time, and so forth. So examples here include maximum matching on a classical computer, integer factorization, as you all know, Shor's algorithm on a quantum computer, and so forth. By the way, just before I get too much further, can you hear me okay? Everything all right?
Yeah, everything's perfect.
Good. Okay, so this is exhibit A. These are the problems we like. And then, of course, when you kind of take a step up the food chain, the next animal you might encounter is something like this, right? Exhibit B, which are the so-called, NP hard or QMA hard problems. These are problems which we think of as being intractable to solve. In the worst case, let me be clear, okay? And for the purpose of this talk, these are hard problems, but I'm going to think of it as, it's a grizzly bear. You probably don't want to play with this thing, but at the same time, it's not really bothering us. It's just kind of hanging out, and life is good, right? So we don't bother it. It doesn't bother us. So here you might have problems like 3-sat classically. And in the quantum setting, you might have something like the so-called local Hamiltonian problem, which I'll certainly mention in this talk later. Okay, QMA, roughly speaking, is just going to be the quantum analog of NP. I don't believe I'll formally define it at any point in this talk, but I'll try and keep it as informal as I can regarding the discussion around this problem. Okay, so that's exhibit B. And for this talk, we're going to not focus on either of these. We're going to take yet another step up the food chain and get to exhibit C. And here the idea is that we're going to think about problems which are even more hard than so-called, NP and quantum NP, but not unreasonably so in some well-defined sense, which I'll tell you about later. Okay, and there's a very specific reason why I've actually chosen to put, two bears in this picture, and we'll get to that later. So that's the main theme for this talk. We're going to be categorizing the complexity of problems. And so the question now is, which problems are we interested in? Okay. So this is the outline for the talk. I'll spend the first little while telling you about the specific problem we're interested in and formalizing that. Then I'll tell you about this really odd looking complexity class, which captures the difficulty of this problem in the worst case. And finally, I'll try and convey a sense of how we show hardness results for this problem relative to this class. Okay. And again, let me be clear, since this is a physics audience, when I talk about problems being hard, I really mean in the worst case. Okay. So that means that if you're trying to solve this problem in general, there are always going to be some really, really hard instances of this problem to solve. But it could be that in practice, many instances of this problem you actually run across will be easy to solve, right? It's not saying every instance is hard. Okay, so let's begin by talking about this problem, approximate simulation. So to motivate this, here you have a picture of, say, your friendly neighborhood physicist, and maybe what she's interested in is a pretty natural question, right? Which is, suppose I have a many-body system X, right? Whatever X is, and I want to know what happens to this thing if I, cool it to low temperature. What properties am I going to see, right? I hope I don't really need to motivate this problem for you, being a physics audience, right? And so, what's the most natural way to answer this question, or at least the most naive way, right? Well, the most naive way to do this is you say, okay, well, I'll just take my system X in the lab and I'll figure out a way to actually cool it to low temperature. And then I'll do kind of the most basic thing I could think of, right? Which is I'll just start making local measurements. I'll just poke this thing, right? And try and extract a bit of information. Okay, that's it. So that's the task we're interested in, right? And the question we're going to ask is, how difficult is it to actually do this task, or to follow this process in some sense, right? Okay, to simulate this task. So let me formally state what I mean by that now, mathematically. Okay. So this problem is called the approximate simulation problem, APX-SIM for short. It was defined by Anderson Binus in 2014. And the basic premise is the following. Is it okay if I say the words like Hamiltonian, just to be 100% careful?
Oh yeah, that's fine.
Good. All right. So imagine now I have a k local Hamiltonian as input, right? K local, remember, just means that each of these terms just acts on k qubits at a time. I have a total of n in my system. And in addition to that, I have some sort of local observable, some measurement in mind, right? This is the measurement I want to make it low temperature. And I have a bunch of parameters, which we'll just ignore for now. And the basic question is, I want to turn this, first of all, I'm a computer scientist, so often we like to phrase everything as a yes or no question, right? Just to make it simple. So I'm going to break this into two cases, basically, right? So I want you to answer yes to this problem if the Hamiltonian I gave you has a ground state with basically nice measurement properties, meaning if I were to measure my ground state according to this local measurement A, the expected value I'll see is small. It's smaller than some alpha, where alpha is some input threshold I chose. Okay, so that's when you answer yes. And no is basically the opposite of this, meaning if it's true that all the low energy states, meaning all the states whose expectation against my Hamiltonian are, at most the ground state energy plus some fudge factor delta, which I get to specify as part of the input up here. For all these low energy states, if my measurement statistics are bad, quote unquote, right? The expectation is large against this observable. That's the formal problem we'll be talking about for the rest of this talk. So maybe I'll take a moment, ask if there are any questions, anything I can clarify regarding this, anything regarding notation, etc.
So if I can ask a quick question here, is finding the ground state not part of the problem?
That's a very good question. We're going to touch on that in a second.
Great.
But in this problem, we're not actually, the output of the problem is not the actual ground state, right? Which you could ask, of course, but you will see it certainly show up. We just want to phrase it as a yes or no question, which is, we're trying to simulate a local measurement just to learn some local information about the ground state. It's a quote unquote easier task than that, at least in principle. Okay, so this is the problem approximate simulation. And what I really want to stress is that we know nothing about this Hamiltonian a priori, the one that's given as input. I mean, I don't tell you anything about it other than the description of it, of course, but I don't even tell you the ground state energy, which is arguably natural because typically computing that is hard to begin with. Okay. Okay. So just some quick selected results here. The very first result on this problem was by Anders and Binus in 2014. And here he showed basically that essentially this problem is what we call complete for this certain complexity class, which I'll define shortly. And the exact definition of complete is not so important for this talk. The main thing that's important is that think of this as it's hard, this problem, meaning that if you could solve this APX-SIM problem in the previous slide, kind of for any input I give you, then you could solve every problem in this so-called class P to the QMA log, whatever that means. Okay, so it's as hard as this class. And the setting he showed it in is when the Hamiltonians and the observables act on just a log number of particles in the system, basically. And what I want to tell you about in this work, basically, is I want to kind of summarize a sequence of follow-up works we did. The first thing we did was we showed that you can bring the locality for these hardness results down. So you can make it so that, even if you're just measuring a single qubit of the ground state, even that's still very, very hard, basically. Okay. And subsequently, we started bringing things down to systems closer to what you might see in nature, right? And of course, you guys are the physicists, so you know much better than I do what you see in nature, but this is me pretending to be a physicist, right? So things like physical model, quote unquote physical models, like the 2D Heisenberg interaction, even if you're on the 1D chain. And most recently, the result we've shown is that even if you're on a 1D translation invariant chain, meaning that I have a system of particles just aligned in 1D, the constraints are identical on this chain. And even then, simulating a ground state measurement basically is very, very hard. Basically, it's harder than quantum NP, and I'll tell you more about that in a second. Okay, so the goal in complexity theory, one of the goals is typically to do this progression, right? You have a general result, and then you kind of make the systems involved more and more closer, look more and more like what you might see in nature. Good. One thing I want to mention is that these works study other problems as well, like things like the difficulty of computing spectral gaps, of detecting an energy barrier in the ground space or in the low energy space. These things I won't have a chance to really tell you about. I'll just mention them very briefly at the end. But for this talk, I really want to focus on this one thread, which is this APX-SIM problem. Okay, so these are the main results. Basically, I'm going to try and give you a very compressed summary about in the about roughly 50 minutes that we have. And to say something about those results, of course, I need to define this complexity class P to the QMA log. So I'll be as gentle as I can, right? The definitions, well, let me show you the definition. So this is maybe for those who are somewhat familiar with any sort of complexity theory, like classes like P and NP. If you're kind of wondering where the story begins, for those who are familiar, let me just very briefly mention that the story kind of begins in the 70s, where originally we had P and NP as these two complexity classes that told us about problems that were easy or hard. And then people start to ask, what happens if you go beyond NP? Like, can we come up with a hierarchy of like classes that can be used to characterize harder and harder problems in some sense? And that's this funny so-called polynomial hierarchy, which has proven incredibly influential. And even after that, at some point, in the late 80s, early 90s, people started realizing that even this hierarchy was just kind of too coarse to capture all the problems we want. And then, so, in your zoo, you introduce more different like partitions of your cages or whatever you want to say, and finer and finer gradations to capture more and more interesting natural problems. And so then you start to see classes like this. And I won't define this. Let me just define the quantum variant that we're going to be interested in. And I'll try and keep this as hand-wavy as possible just to keep it high level. So what do I mean by the class P to the QMA log? Okay, the class P to the QMA log is a set of all problems, roughly speaking, that can be solved efficiently on a classical machine. So a P machine, a polynomial time machine. But there's a catch. The catch is that you have this magic ability. The magic ability is that you can call a so-called QMA oracle. Okay, so roughly speaking, what that means is that you can magically get the answer to a ground state energy problem, meaning you can give me a local Hamiltonian and I will essentially tell you what the ground state is. And you can do this, a ground state energy is, sorry, and you can do this a log number of times. Okay. So that's the basic premise of this class. It is a completely unphysical class, of course. Such a machine certainly cannot exist. We don't believe you can solve these types of QMA problems efficiently in any sense. So, obviously you're not going to be able to simulate this oracle in any sense. But the point, that's not the name of the game, right? The name of the game is we're trying to really understand the complexity of solving certain problems. And as kind of ridiculous as this class looks, right, it certainly has a marketing problem, right? The truth is that it's going to end up capturing this very natural problem, which is this approximate simulation problem. Okay, so you have to go where the problems go in some sense. So any questions about this statement first?
So how does this differ with just P to the QMA rather than P QMA log? Is this
Good.
in the normal QMA specification? You can use as
No.
many queries as you want, or?
Good. So if I just said P to the QMA, then you could use as many queries as you want, limited only by the runtime of your P machine. But since we're talking P to the QMA log, the log means this log here, that you can only solve a log number of QMA queries or QMA instances, let's say. So it's restricted in that regard. Okay, so let me tell you a little bit about this class, just to give you a feeling for it. So first, let me just mention very briefly that we believe this class is certainly harder than plain vanilla QMA, and roughly speaking, the idea is because you can fit both QMA and its complement into this class. I don't want to say much about that in the interest of time. So it's believed harder than QMA, but at the same time, as I said in the opening of this talk, it's not too much harder. Okay, and we can show essentially the best previous upper bound that was known on QMA. So previously QMA was known to be contained in this funny class PP. We can cram this P to the QMA log in the middle, basically. So it's not too much harder. Again, the definition of PP is not so important for this talk. The one thing I will use in this talk, and I'll come back to this later, is that there's a question of how many QMA queries am I allowed to make? And I answered you can make a log number, right? But it turns out you can have a trade-off. The trade-off is that these log queries are in some sense very powerful in that they're allowed to be adaptive, right? So I can make one query, I can give you some Hamiltonian and you tell me the ground state energy, right? And then based on that, I adaptively decide what my next query is going to be. But if you're willing to give up the adaptiveness and make all the queries in parallel, okay, so you compute all the queries ahead of time and you make them all in one shot, then it turns out that this class is completely equivalent to making a polynomial number of queries, but now non-adaptively in parallel. Okay, so you can think both are equivalent, and it'll turn out to be very fruitful to think in this picture. Okay, so we'll make more queries, but they'll be non-adaptive, so they'll be kind of all in parallel. I'll come back to this later. So this is the class P to the QMA log. Now, let me mention, as was also alluded to in an earlier question, why P to the QMA log, right? It's a really funny looking class. Like, where does this come up? Why does it come up, right? So the answer fits on one slide. It's actually quite simple. So the reason is because it comes about when you try and prove that this problem can be solved by a machine of this type. Okay, a polynomial time machine, which can make a log number of QMA queries. So let's see how that works. So proof sketch. What was the problem? The problem, remember, for APX-SIM is I give you a Hamiltonian, I give you the observable, and your job is to estimate for the ground state of your Hamiltonian, what are these measurement statistics, right? That's roughly the goal. Now, here's the problem. If I don't know what the ground state energy is ahead of time for H, how in the world can I identify this ground state, right? Even if you gave me a copy of the ground state and you said, aha, here, I promise I'm being honest, this is the ground state, how would I ever believe you, right? I don't know what the ground state energy even is to compare it against, right? So I can't like run phase estimation or something. So the obvious thing we first want to do is we want to estimate the ground state energy. And that we can do quite easily given this QMA oracle. Because with a QMA oracle, I could use a log number of queries basically to essentially do binary search over the energy space to basically zoom in on what is the correct ground state energy of my Hamiltonian. Okay, so I lied slightly in the previous slide. Every time I call my QMA oracle, it doesn't tell me the actual ground state energy of my Hamiltonian. It tells me, yes, the ground state energy is, below some threshold, or it says, no, the ground state energy is above some threshold, right? So it allows me to kind of cut my search space in half, basically, and either go down or up in my search space. And so by doing log n queries, I can get an estimate of the ground state energy up to, plus or minus some fudge factor. And now once I have this estimate in hand, now life is good, right? Because basically you can now give me a copy of the ground state, right? I have an estimate of the ground state energy. So, I can choose to check that indeed the energy of your state is roughly what I think it should be, right? Or at the same time, I could flip a coin, and otherwise I could do the measurement check to check that the measurement statistics are correct. Okay. So the point is that the reason why this class comes up is because we use this log number of queries to the QMA oracle to first figure out the ground state energy. Okay, that's essentially where that log factor comes from. Okay, so that's why we care about this class. Any questions about this slide first? Okay, 23. So maybe I'll go through this very quickly. It's not super relevant necessarily for the high level understanding of this talk, but I do want to point out one thing that we tend to worry about as computer scientists, which is that this class QMA is a class of so-called promise problems, right? And what that basically means is that, well, let me show you the next slide. You have to be a bit careful when you play with this. So here is the so-called K-local Hamiltonian problem, which is every time you query your QMA box, right? This is the problem you're asking, right? You give me a Hamiltonian, you give me some thresholds alpha beta that are separated by some 1/poly gap. And the machine's job is to tell you, yes, the smallest eigenvalue is at most alpha, or it's at least beta. And those thresholds are separated by a gap. And now we're in this funny world where I have this P machine that's making queries to this magic box, right, that claims to solve this problem, right? And so how do I know, right, if I as the P machine, when I come up with my Hamiltonian, like how do I know that the ground state energy really satisfies this promise, right, that the ground state energy is either at most alpha or at least beta, right? How do I know that lambda min is not between those thresholds? And the answer is that, well, we don't know. The P machine has no way of knowing this, right? It's QMA hard to solve for ground state energies. So we needed some way to deal with this. And so in case you're wondering how one deals with this, well, we formally define it so that every time you query the oracle with a bad Hamiltonian in some sense, which violates this promise gap, then the oracle can do whatever it wants, right? It can answer whatever it feels like, and that's fine, right? It makes a model well-defined. The only problem, of course, is that the P machine is making queries to this box. It has no idea if it's making these so-called bad queries to the box, so it doesn't know if the answers it's getting back are arbitrary. And so at the same time, its queries in the future might depend on previous bad answers it got in some sense, right? So somehow its final output of the P machine should be well defined, right? Even if these boxes give me like bogus answers because I asked them bogus questions, right? And the way we get around this is that we formally define it away, right? So to be a valid P to the QMA log computation, you always have to output the same answer regardless of how any kind of bogus queries are answered. So you have to be sufficiently robust in some sense. Okay, and this is actually an important point. It is one of the more subtle but finer points that makes it a little bit tricky to deal with these types of classes where you have, say, P to the QMA or something like this. So you're making oracle calls to a promise problem. I think that's all I want to say about that promise stuff. But for those who are interested, this is just a quick side point. Okay, so let's focus in the remainder of the talk on how you might show P to the QMA log hardness. Okay, so let's just take this step by step. Okay, what is our goal? Our goal is to show that, if you could solve this approximate simulation problem kind of on arbitrary inputs, then you could solve, or you could simulate kind of any computation from this class P to the QMA log. So a P machine making a log number of QMA queries. Okay, you could always simulate that. So how do we show this, right? So here are the steps at a high level. So in other words, imagine I give you some arbitrary P to the QMA log machine M. So this is a polynomial time machine, right? Making QMA queries. It takes some input X, and given the input, it's going to output some answer, yes or no. And so what we're going to do to show this hardness result is we want to take the machine and map it to a local Hamiltonian and to an observable, okay, plus some threshold, so that if M accepts X, then H has a ground state with nice measurement statistics, right? And otherwise, if M rejects X, all the low energy states have bad measurement statistics. Okay, so this was just the APX-SIM problem. So in other words, we want to map a yes case of the machine to a yes case of our APX-SIM problem, and a no case of the machine to a no case of the APX-SIM problem, right? So if you can answer APX-SIM, then you could certainly tell me what the machine was going to do on its input. That's the basic premise. So anytime, by the way, somebody says we want to show a hardness reduction, this is ultimately what's happening under the hood, this type of thing. Okay, so in this particular context, what are the challenges we face in showing such a hardness reduction? So the first challenge is, well, I'm taking a machine, a computation, and I'm embedding it into the ground space of a Hamiltonian, right? So, how do I read out the answer to the computation via this observable A? That's one question. The second and more troubling one is that, the definition of P to the QMA log, it's not even physical, right? I mean, this QMA box is some magic device that doesn't actually exist in real life, right? So how in the world am I going to take this thing and embed it into a ground space, right? Which is some explicit object you're giving me in some sense. And finally, I touched on this on the previous slide, which is, remember, the machine M can be stupid if it might accidentally make kind of bogus or invalid queries which violate the QMA promise. And so you do have to deal with that, but in this talk I won't really focus on that too much. Okay, the main challenge is typically the second one. So I'll try and answer these three questions though in the rest of this talk. Okay, any questions about the setup? Okay. So over the years, there have been two frameworks that have come up to show these types of results, and I'll try and tell you a bit about both, how they work basically, and what are the pros and cons of each basically. Okay, so the first setup dates back to Andres's original paper. So here he had the so-called query Hamiltonian gadget. And more recently, we've developed this, what's ultimately become this flag qubit construction that I'll also tell you about. Okay, and I'll let you decide which CAD is which framework. Okay, so before I tell you about either of the frameworks, at some point earlier I mentioned that it will be very helpful for us not to imagine a machine that makes a logarithmic number of adaptive queries to a QMA box, but rather a machine which is a little bit quote unquote dumber. It makes non-adaptive queries. It just makes them all, pre-computes them ahead of time and makes all the queries in parallel. But now it can make a lot more queries. It can make a polynomial number of queries. So, to help visualize this is going to be the framework we're going to work with. So I'm going to assume my computation for P to the QMA log really looks like this now. So what is this picture saying? In words down here, this is what it is, but let me explain it. So what the P machine will do is it will compute some polynomial number of inputs to a QMA oracle. So each of these is a local Hamiltonian, right? And it's going to ask a ground state energy question. And it will plug them all in parallel to these QMA magic boxes, which don't exist. And then the answers will come out, right? And now this is just some classical post-processing that the P machine can do, so that based on the answers from the QMA boxes, it will output a single bit saying, yes, I accept, or no, I reject. Okay, so henceforth, this is my picture of a P to the QMA log computation. This is what I'm going to work with. So we're starting with this kind of computation, and we want to embed it into a ground state problem where measuring the ground state will tell you the answer to what would have popped out on this wire. Okay, that's what we're going for. So let me tell you about the first framework first. So this framework is due to Andres, and it's a very nice framework. It's very elegant, very slick trick. And I'm going to show you the very basic premise of this gadget, basically. So let's imagine for a second, we're just going to make a single QMA query. Okay, and QMA query, again, means I'm just giving you an instance of the local Hamiltonian problem. So I'm going to give you a Hamiltonian H. To build this gadget, what do we do? Well, we introduce two spaces. One space X is just two-dimensional, so it's going to, in principle, it's supposed to hold the answer to the query, which is either yes or no. Yes, there's a small ground state energy, or no, the ground state energy is high. And the second space Y is supposed to hold the so-called witness, or the actual ground state of H. Okay. And so this is the premise, right? Either my Hamiltonian is low energy, or it has high energy, right? That's the starting point. And so Andres constructs this very slick gadget, which is basically what it is as follows, right? So in the X register, this is the answer we want to encode, basically in the X register to the query. And to force the answer to really be 0 or 1, the right answer, we'll couple it with these two operators here. So H here is the actual Hamiltonian that we're trying to resolve the ground state energy of, and I is just the identity. Okay, alpha plus beta, this is the average of the two thresholds. And if you want to write this block diagonally, well, it looks like this. It's literally a block diagonal matrix. Okay, so you might be staring at this and wondering, why in the world does this work? Right? Why does it encode the answer to this query? So yeah, it's very cute. In the S case, what do we know? We know that the Hamiltonian H has a low ground state energy, like the threshold is at most alpha. And so if I stare at this Hamiltonian, right, I mean, it's easier in this block diagonal form. If I look here, right, where is the lowest eigenvalue of this thing hiding, right? Well, in this identity block, the smallest eigenvalue is precisely alpha plus beta over 2, whereas in this block, it's strictly smaller than alpha, right? So certainly it's hiding in this block, the smallest eigenvalue. And well, this block is the one that's tagged with a 1, right? And so what that means is that the ground state certainly has a 1 in this X register, right? So it's encoded the answer 1 now on that register. And conversely, if my smallest eigenvalue was large, it was at least beta, then the smallest eigenvalue, now if you look at this encoding, right now the smallest eigenvalue here is large, it's at least beta, right? And certainly the average is going to be smaller than beta. So now the smallest eigenvalue is hiding in this block. And what that means is that, again, you'll be tagged in the X register with a 0, ket 0. Okay, so in this way, we can encode the answer to the query with respect to the ground space in this X register. Okay, the ground space will exactly tell us what the answer was to the query. This is the basic query gadget. This is just for a single QMA query, this thing here. And now, of course, we can take this thing and stitch it together when you make more queries. So let's show how to stitch it together. So in Andres's original paper, he was dealing with adaptive queries, so it looks slightly messier than this. But since we now know that we can do everything in parallel, it'll make our lives a lot easier. Because essentially, if I'm making m queries in parallel now, they don't depend on each other. So I could just independently just add a bunch of terms together. And each of these terms in the sum will correspond to a different query, right? They're all independent of each other, so I could just sum them, right? There's no dependence here. And if you don't fully follow this expression, don't worry. I mean, at this point, the most important is the previous slide, which gives you a sense of how the gadget works. And on this next slide, I'm just trying to give you a high-level sense of how you stitch things together. But obviously, in the interest of the time, I won't spend a lot of time on this slide. So you can, put together a Hamiltonian, which I'll call HM minus, so that the ground state of this one encodes the right sequence of query answers in, these X registers. And, basically, what we can say is, roughly speaking, when you put this together, you can prove formally that the ground state of this Hamiltonian, basically, if I think of it as, the joint Y space and then the joint X space over here, the ground state in the X space will be a sequence of bits which perfectly encodes the answer to all of your QMA queries. Okay, so that's all you kind of get out of this construction, right? So make sure that the queries are answered correctly. Okay, I won't go more into this actual lemma. One thing I will very briefly say is that you might wonder if the correct sequence of query answers is unique, right? And the answer is, if you think about it for a second, it might not be, right? Because remember, you can make these bogus queries by accident, and then the oracle might answer 0 or 1 arbitrarily, right? So the correct sequence of answers might not even be unique. And so what does that mean in terms of, energies, the low energy space, right? So what you have to be careful about proving is, so I'll show you on the next slide now, is if you kind of try and visualize the spectrum of this Andres's gadget, basically, the best thing you could really hope to show is that there exists, the ground state really will indeed capture a correct sequence of query bits, right, including some potentially bogus answers. And the first kind of incorrect query string, meaning where at least one of the answers is wrong, that will have an energy gap from the true ground state energy, right? And in between, you could have all sorts of degeneracy in terms of other query strings, which might be still correct. It's just, you had a lot of freedom in these bogus answers and how they could have been answered. But at least all the non-bogus queries were answered correctly. So this is just some of the technicality that comes out of dealing with the fact that it's a promise problem. But, let me not focus more on this. Okay, so from this slide, we can force the correct query bits to come out of this X register. And now let's see how we use this gadget. Okay. So this is kind of the high-level overview of how you use that gadget to get a final hardness result. So let's imagine, let's picture for a second the memory of this P to the QMA log machine M, right? So what does it have? Well, it's going to output its results somewhere. So let's call that C. It's got some workspace, right? Let's call that B. So ancilla qubits. And here we'll imagine that it's storing its QMA, the query results. Every time it makes a query to this magic box, it gets a bit and just kind of stores in the next cell. Okay, that's the memory. And the first trick we'll play is kind of standard in classical computer science, except usually it's in the framework of randomized algorithms, not making queries to an oracle. And the trick is that, let's assume for now that the machine here, instead of making queries to this magic box, instead somebody just gives it all the answers to the QMA queries, just kind of as a string in one shot. Okay, so it doesn't actually make queries, but some as input essentially, or as a proof, if you will, somebody tells me what the answers to these queries should be. And for now, let's just believe that these answers, these bits are correct. Okay. Of course, a priori, that's not necessarily true. Okay, so we'll assume that we'll get the bits as input rather than making the queries. And so what is the next thing we do? Well, if we think of this as being a proof register, then what you could do next is you can apply, for example, Kitaev's standard history state Hamiltonian construction. And if you don't know what that means, that's fine. I mean, the basic premise is that, given any quantum circuit, you can apply a history state construction to map it to a Hamiltonian, right? So that the structure of the computation is preserved in the ground space of the Hamiltonian. Okay, roughly speaking, that's what this thing does. Okay, so in other words, we can force the ground space of this Hamiltonian I construct through Kitaev's construction to simulate this funny modified machine, which takes in a proof of query bits. And now the thing is that while this only works correctly, the answer only comes out correctly here if the person who gave me this proof, who claimed it was the correct query string, really was being honest, right? I wasn't able to force this to be the correct query string, and so how do we force it? Well, this is where that Andres's gadget comes in. It turns out you can stitch these two together so that this will force the A space to indeed encode the correct query string. And then when you plug that into Kitaev's Hamiltonian, then this one will make sure that the computation proceeds correctly. And so that means that on C we'll get the right answer. And now, of course, in the ground space, if I make a single qubit measurement just in the standard basis, right, it'll tell me the answer to this original machine's computation that I started with. That's the basic premise of how to use the Andres's query gadget to get one of these hardness results. Okay, so for clarity, what I've shown you is a blend of the first two papers in the list of papers I showed you, Andres's gadget plus the follow-up work we did to get locality down to single qubit measurements, for example. Okay, let me very briefly tell you about pros and cons of this thing. Pros are that the ground space really will genuinely encode correct query answers. And roughly, this is just because remember in Andres's gadget, this thing was block diagonal, right? So the ground space really lived in like the cheapest block in terms of energy. The problem is that it's hard to take this thing and use it when you want to start thinking about geometrically constrained Hamiltonians and showing hardness for those. Okay, so that's what the second framework is going to be good for. So let's move in the remaining time to the second framework. So in the second framework, we want to kind of push further, and we want to say, what happens if we start thinking about Hamiltonians, say, in 2D or on the line, in 1D? And so for the first result here, basically, we first showed hardness basically if you have a 1D chain of 8-dimensional systems. These are not translation invariant, okay? And here is kind of like a preliminary version of this idea, basically, which we call the sifter construction. But more recently, we were able to refine it further to get to a point where really now it's like a full-fledged framework, which we call the flag qubit framework. And this thing gives us two nice things, which I'll try and stress. Number one is extremely flexible. So as I'll try and stress, it really gives us a very kind of abstract or black box way to say, give me your favorite circuit to Hamiltonian construction, and I will show you how to get a P to the QMA log hardness result as a black box lemma almost. Okay. And one of the applications will be that we'll be able to show that even if you have 1D translation invariant systems, simulating measurements on the ground space is still very hard. Okay, so the basic premise is that we're going to push as much as possible to the circuit side before applying a circuit to Hamiltonian construction. I'll tell you more about that in a second. And there's some counterintuitive There's a counterintuitive idea that comes into it, and maybe I'll focus on that when I get to it. Okay. So in a very, very brief slide, essentially, this is the heart of the construction. Okay, so what is the idea here? Okay, it's a very different approach. The idea here is as follows. So remember that what I'm trying to do is I'm trying to simulate the behavior of this P machine, which makes a bunch of QMA queries in parallel and then does some classical post-processing. Okay, now I want to simulate this in the ground space of Hamiltonian. So again, I don't have access to this magical QMA box. Previously, we got around that by using Andres's query gadget. Now I don't want to use the query gadget, right? Now I want to do something a little bit more kind of explicit. And so what I'll do is, instead of querying the QMA box, I'll literally put in a so-called Qma verifier. Okay, so replace the QMA Oracle query with a QMA verification circuit. Now, I don't, in the interest of time, I don't really want to define QMA for this discussion, but of course you're welcome to ask me. But roughly speaking, what is a QMA verifier? Just think of it as a polynomial time quantum circuit. That's what this is. And the only difference between this and say BQP is that here, not only do you get the input, which is Q, but you also get a quantum state as a proof. Okay, and the job of this is to verify the proof. Okay, so if you give me a good proof, it should output 1. If no good proof exists, then it should output 0, right? That's the basic premise. So instead of calling these magical Oracle queries, which I can't do, of course, instead I'll imagine that I have verifiers for actual, QMA verifiers kind of on the ground, right? And each of them will take in some corresponding proof, W1 through Wn. In this picture, I've drawn them as a tensor product state, but of course, they're in general, they're not going to be a tensor product state. And what do I do? Well, given the output qubits here, these should tell me the answers to the queries in theory, as long as you gave me the optimal proofs. If I post-process, this thing will give me the answer to the computation. Now, I have no way of forcing somebody to really give me the right proofs here. And so to get around this, what we do is we insert these conditional rotations here, right? So this is just a rotation that's going to take my ket 0 state and rotate it slightly towards 1 by some angle here, right? I mean, it's not so important here. And we'll do this on each wire. Okay. So this I explained. And so this is what I just explained. So this is the basic framework. And now the question is, why in the world does this do anything interesting, right? I mean, all I did is I put down verifiers and I kind of did a conditional rotation on each answer. Okay. So there are two output wires I'm going to focus on, the output qubit and the flag qubit, right? Which is where these conditional rotations happen. So let me tell you why this works. So first, let me really clarify that if you've ever kind of studied these QMA type proof systems, typically if you run a bunch of these in parallel, without loss of generality, you could always assume that the best strategy is to just give me the best proofs locally on each verifier. That does not work here. Okay, that's actually false, right? So it might actually be in a cheating prover's interest here to give me a bad proof on purpose that would, flip the answer here, which may ultimately cause this post-processing step to flip its answer. Okay, so it's not true a priori that the locally optimal proof is the best strategy here. Okay, so why does the flag qubit allow us to really force the local proofs to be optimal? Okay, so that's what this is asking. And so here's the basic premise. So now that I showed you this big circuit, this big super verifier on this previous slide, now is when we take all of that and we shove it through, your favorite history state construction. Let's just pick Kitaev, but you could always pick something, say like the Gottesman-Irani 1D translation variant construction, which is one of the things we use in our paper. And so from that, you map that super verifier V onto a Hamiltonian H, and H will have certain encoded qubits basically that it acts on that correspond to the wires that came out of that circuit, essentially, right? So there'll be some qubit that corresponds to that flag wire, this one over here that came out of here. And so what we're going to do is, roughly speaking, we're going to penalize that flag qubit. We're just going to put a single qubit penalty term on it. Okay, that's it. Why does this work? So let's go back to this picture to try and explain why this works. Right, so we're just going to, once we're going to take this thing, we're going to push it through to a Hamiltonian construction. And in Hamiltonian world, on the Hamiltonian side, we're going to penalize the, the encoded version of this qubit. Why does this work? Why does it force these proofs to be correct? So every time this, let's say each of these queries is answered correctly, we rotate slightly from 0 towards 1, right? That's what this is doing. That's what this is saying. But now when I move to the Hamiltonian side, I'm penalizing the answer 0, right? So I'm encouraging you to rotate as far as possible towards 1 on this qubit to minimize your energy penalty. And of course, then intuitively, you would then expect indeed that all these proofs are going to be as good as possible so that you'll do the maximal rotation here possible. Okay, so you go from as close to a 1 as possible on this flat qubit. That's the very basic premise. So to make this formal take some work, let me just mention one thing that's really neat here is that there's something kind of, if you sit back and think about this, it's a bit counterintuitive, right? Normally in quantum information, we are not allowed to take m bits of information and cram it into a single qubit and expect to be able to extract anything meaningful back out of that single qubit. Okay, it just doesn't work. Like if you think about something like Holevos bound or Nyax bound or something. But here, we're taking m of these bits, right? And somehow we're cramming them all into this one flag qubit wire and still making use of it. So it's a little bit counterintuitive. Okay, but let me just briefly say that to formalize this claim on this slide, right, that by penalizing this flag qubit, we can really force all these proofs to be optimal and hence the QMA queries to be answered correctly. We need a technical lemma for that. Basically what this says, obviously I do not expect you to parse this in the time we have, but the basic premise is that, if the ith proof is, epsilon suboptimal, then we can prove a rigorous kind of deviation bound, right? This is basically saying that then you'll be off from the ground state energy by some lower bound that scales like 1 over poly the system size. Okay, so what I really want to stress here is that, if you just want to argue that locally the terms, once you put in the flag penalty, that the locally optimal proofs are optimal, that can be done using standard techniques. What is non-trivial here is to really give an analytic rigorous bound on the exact deviation. Okay, so that's kind of where the work comes in. And the challenge here is, of course, these proofs that you're plugging into the circuit, they can be entangled in general, right? So when I do this measurement, it can disturb the next proof. And so you have to be careful how you need to use conditional probability very carefully to make sure that you get the rigorous bound you want. Okay, but let me not say more than that in the time we have. Okay, so basically the upshot is that we can force, just by putting the single qubit penalty on the Hamiltonian side, I can force all m of these QMA queries to be answered correctly. So it's a bit magical in that sense. And so why did we go to all this trouble, right? Why did I do this funny thing where I'm cramming these mQMA queries into a single qubit? Like, sure, maybe it's cool, but what is it? What's the point, right? So the point is this, right? And I'm not going to sit here, obviously, and again, expect you to memorize this, but very briefly, what this slide is saying is that we get a very kind of high-level abstract lifting result, which is that you can take essentially an arbitrary computation. It doesn't even have to be from this class P to the QMA log. We can actually think about much more general base classes D instead of the class P. And instead of QMA, we can think of a much broader class of quantum verification systems, Q. I won't really define them for this talk. So you give me your favorite class D to the parallel Q, whatever that is. And you get to pick your favorite local circuit to Hamiltonian mapping. And maybe you choose the one that is very nice for you because it has certain nice geometric properties, for example, like your Hamiltonian comes out looking squished in a certain way, or it has certain properties like translation invariance. Doesn't matter. I don't care. You give it to me as a black box. And I will output for you a construction basically that encodes the hardness of your D to the parallel Q problem into this ground state energy measurement problem in a Hamiltonian, which satisfies all the lovely properties of your black box circuit to Hamiltonian mapping HW. Okay, this may look messy, but there's really only one free parameter you need to adjust in order to use the lemma. It's this alpha. And I won't say any more about this slide. Okay, so I just have a few minutes. Maybe I will skip this one. This is just trying to tell you what are the basic requirements we need on the classes and the mapping, but let me not say more about that. They're quite mild, the assumptions. As I mentioned, the pros of using this flat qubit construction is that because the only thing I'm doing on the Hamiltonian side is just a single qubit measurement, essentially, I really preserve the structure of your Hamiltonian. Okay, I don't need to add a bunch of stuff once I move to Hamiltonian world. And we get this very nice black box lifting framework. One thing I want to mention is that right now this framework requires error reduction. So it doesn't apply to a class like stochastic MA. Technically, we have a solution for this now in forthcoming work, but let me not say more about that. Okay, and another thing that let me very briefly mention, these works also study other problems which are of interest, things like estimating spectral gaps, two-point correlation functions, this ground state connectivity problem, which is asking, does your low energy space have an energy barrier? Okay, all of these can be captured using kind of similar tricks. Okay, the complexity. Okay, so let me move to conclusions. We talked about the complexity of simulating measurements on ground spaces. We said that this is harder than quantum NP, and it's complete for this odd-looking class P to the QMA log. We showed two different frameworks for showing this hardness. And kind of the overarching themes were that, this class, which, certainly looks like a so-called ugly duckling, if you will, it captures extremely natural problems, right? What are you going to do about it, right? This is the right class. And along the way, we did some funny things like cram m qubits of information in some sense into a single qubit, along the way obtaining a generic lifting framework. Some open questions. So can we make the flat qubit construction work without error reduction? So technically this is not so open anymore, but let me just put it here. But one thing I think that we really try to do this work is that we really like that this work is black box in the sense that it gives you, you tell me your favorite circuit Hamiltonian construction and we can kind of bootstrap it to get a hardness result. And it would be really nice if more, generally speaking in this field, we can kind of take this approach, because a lot of times what happens kind of necessarily so in the field is that somebody will show some sort of hardness result, and then, to get it down to say a 1D chain or something like this, you really kind of have to tailor customize your constructions, right? And wouldn't it be nice if you can kind of do things, once you get the hardness in the original setting, if you could just kind of plug in your favorite Hamiltonian construction and then bootstrap that to get a hardness in a more desirable setting, like a 1D setting or something like this, right? So I think this would be a nice direction in general for the field moving forward. Okay. Those are my conclusions. Finally, if you're interested to learn more about this kind of stuff, there are various surveys on Hamiltonian complexity, which you're welcome to look up. If you're interested in learning more about introduction to quantum computation from a computer science perspective, or more advanced quantum complexity theory, we certainly have open access lecture notes, videos on YouTube. So you're just welcome to just Google our lab page or look up our YouTube channel and look up that stuff. And with that said, thank you very much for your attention. And that's it.
Okay. On any questions, either you can raise your hand or you can just unmute yourself. Okay, so I noticed some questions also asked during the talk as well. Maybe I'll wait 5 seconds more for.
Oh, sure, that's fine.
Okay, so maybe let's thank Professor Gharibian again. A very nice talk.
Great.
Okay.
Should we close?
Yes, let me